more about category theory. So I'm a little bit biased, but I think it's fair to say that category theory is the most important mathematical tool that we use in theoretical computer science. It really touches on all aspects, I think it's fair to say, of theoretical computer science. So these lectures are designed to give you an introduction to category theory, how to work with it, what kind of things you can do with it, and in the end, I think I will try to move towards making connections with other lecture topics that you've seen in the school. So, we're talking about category theory. And the first question, I guess, is what is category theory? Like, what are we doing when we do category theory? So the first answer that I would like to give is that really from a mathematical perspective, sometimes mathematicians, they, I don't know, are interested in particular differential equations and solving those differential equations, things like that. Those are problems and solutions that are really about looking at like one particular thing, some manifold with some dynamical system on it or something, and understanding the behavior of a tiny particle in that one particular thing. Category theory is very different. It's about understanding mathematical objects only via the relationships that they have with each other. Okay, so it's about understanding mathematical objects. So by mathematical objects, I mean like objects that we are treating mathematically, but of course, especially in school, those mathematical objects are often things coming from computer science. So understanding mathematical objects via the relations they have with each other. So I would call this an external view. Like in the sense that we have a bunch of mathematical objects, and we just look at how they interact with each other. We're not allowed, or we're not able to, with the formalism of category theory, to look into one particular object and understand what's going on inside one particular object. We just see all the objects together and how they interact. So it's an external view, not an internal view. So that's the first answer. And I don't want to erase the Zoom link, so I'll go over here. So then I want to give a second answer. So since we are understanding mathematical objects via the relationships that they have with each other, what we're looking at when we're doing category theory, so looking at a category, we'll define that in a second, a category of the mathematical objects in question and the relations between them. So something kind of like a graph, but with a little bit more structure. And so we might have like the category of all groups, or the category of all metric spaces. So the thing that mathematicians care about. In computer science, we might have the category of programs, or the category of programming languages, or something like that. Category of automata, stuff like that. So we understand a whole mathematical or computer scientific subject via its category, like there are group theorists, we have a category of groups. There are topologists, we have a category of topological spaces. And then we can compare those different categories. So we can say that certain categories are equivalent to each other, or certain categories have some kind of relationship to each other. So for instance, I think in several of the lectures that you've listened to already, you've heard about the Curry-Howard correspondence. And the way to make that correspondence mathematically precise is to say that you have a category of simply type lambda calculi and a category of Cartesian closed categories. And those two categories are equivalent. So these domains, like domains of study, simply type lambda calculus and Cartesian closed categories, are equivalent. Okay, so the second answer, to sum that up, is that we can compare domains of study. Because the thing composed of this, the object and the relations and the category, encapsulates the whole domain of study. Okay, so those are my two answers. Now I want to pose another question, which is, what is a category? So, in category theory, no surprise, the main thing that we study are categories. So, here I'm talking about mathematical objects. The mathematical object in this theory is category. So what is a category? So I'm going to define it in a few minutes more precisely and rigorously. But right now I just want to define it very roughly to give us some intuition. So roughly, category consists of two things. It consists of a collection, it's probably too small. A collection of objects, like these mathematical objects, and a collection of what I called over there relations. But I'm not going to use the word relation anymore because that maybe when we started getting technical, that kind of refers to something more specific. A collection of what we call morphisms or maps between them. Okay, so so I use the word relations because that's good intuition, but when we get technical relations, we'll be certain kinds of morphisms or maps. We won't use that word again very much. Okay, so now it's time for some examples. So maybe the favorite, oh yeah.
Can you see empty? Like if you have no objects and no morphisms, is that category?
Definitely. Yeah, okay, so I used the word collection to be, I also want to say something about this. I use the word collection to be vague. I'm also going to be vague in the more technical definition. You could take these to be sets. So definitely the empty set is fine. You could also take them to be types, like in Anya's lectures last week. So I want to be foundation agnostic, because some people like to do their math and set theory, some people like to do their math and type theory. I use the word collection to not choose one or the other. That's something like the type or set. Okay, so what are our favorite examples of categories? Maybe the first one that you always see is the category set. So when I write categories on the board, it will always be in a curly font. I kind of hesitate because I think all my writing is a little bit curly. But I will try, especially for set, I have this move here. That's trying to know a category. And if it's not clear what the category was, not a category, just ask me. So set with this curly S consists of objects, sets, so we take as objects, the collection of all sets. Now maybe the fact that I'm using the word collection also lets me sweep under the rug problem. We talk about the set of all sets, right? So there's some kind of size distinction there. So we have the collection of all sets, those are the objects, and the morphisms are functions using sets. Yes?
Do the sets contain anything but sets?
What do you mean by that?
Are these sets of numbers, or sets of dogs, or are you agnostic about that?
So if you want to be really precise, maybe you take your favorite set theory, like ZF or ZFC, then you consider the collection of all sets that you can generate from that theory, and those are the objects in this category. Yeah, there's another category that I might not write down, which consists of sets as the objects and relations between sets as the morphisms. So that's why I didn't want to use the word relations more generally.
of sets.
Sorry?
I believe there's something called the small category of sets. And I was wondering if you could cover that just a tiny bit. Like, why do they call it the small category of sets?
So a set is definitely a large category. And that distinction of small and large is about the collection of objects here. So if we consider the collection of all sets, that forms a proper class. Doesn't form a set. If it did, we would have some paradoxes on our hands. So that forms a proper class. So set is definitely large. You could maybe try to wiggle yourself out of that if that's a problem for you by restricting the size of your sets at some cardinal. And just take all the sets that are smaller than that, and then you would have a small category of sets. A small category of sets that are smaller than some given cardinal.
Okay, that's perfect, thank you.
Yeah, that's maybe where you've seen that.
I've heard of the word arrow in the context of categories. Is that morphisms?
Yes, yes. Maybe I'll write that here. Yeah, maybe my favorite word to say is probably maps. I'll probably say that the most, and then morphisms and arrows. Yeah, any other questions? Okay, so the most basic example maybe is the category of sets. Now, especially in this summer school, maybe our favorite example is the following category. So now I need to make the P curly, so my attempt at a curly P. Prop. So this stands for proposition. And the objects here. Okay, so to be clear, we haven't done anything very formal yet. So just like for set, I haven't fixed a particular set theory, like the Mello-Frankel set theory or something. I was assuming you can pick one, and then we'll produce a category. For prop, I'm thinking about any kind of logical system, maybe first order logic, as defined by method reduction, which I think you saw last week, would be a good one. That will give you a category where the objects are the propositions defined by your logic, and the morphisms, or arrows or maps, are given by, if you want to be really precise, derivation is the right thing to talk about, but usually derivation is equivalent to implication in most logics. So we want to say that two propositions are related to each other in the sense that we're studying a category theory if one implies the other, or if you can derive one from the other. Okay, so what else do I have here? So then we have the category of types to take. Again, I leave it up to you to define or to specify the specific type theory that you're interested in. Here, the objects are the types in whatever type theory you like, and the morphisms are, again, something like derivation, if we want to be precise, maybe just write derivation, by which I mean like from the concept P, maybe you can derive that Q holds, or that there's some term witnessing that Q holds. And in most type theories, this is equivalent to having a function from P to Q, like the one that Anya described to you. Okay, so we have tie. Maybe before I give more computer scientific examples, I'll give some original examples that people invented category theory to do. So we have the category group, so maybe I should make that more clearly. The category group, which has objects groups. These are not going to come up in the rest of this course, so if you have some mathematical background, you know what a group is. They definitely form a category. The morphisms are group homomorphisms. So the natural thing like a function but for groups. And we also have top, which consists of topological spaces as the objects, and continuous functions as the morphisms. Yes?
This question about the type category. You're probably going to say no, but is it equivalent or isomorphic to the category of, would that be equivalent to universes or type universes, or would universes form a separate category?
Yeah, that's a good question. So when we have a category of types, so the Martin left type theory defines one of those stuff which assembles into a category, like I've described here. So that's a category. The universe is itself a type. So it's an object in a category. So it doesn't naturally form the structure of a category itself. It's just a type. It's not a category. So it's an object in a category. But then you could say, I mean, usually the type theory sets up some kind of correspondence between the universe and the overall category of the type theory. Yeah, so that's something to work out. But a priori, they're different kinds of things. Yes?
I have a question about the group category. So the homomorphisms, those like go from a group to the same group, right? So it just says that none of the groups are like you're not like relating any two groups together with that, or are you?
So a group homomorphism. So like the groups could have a group like G, a group H. Maybe our favorite group is like the integers. Another group is the real numbers. I don't know. For addition or multiplication for the real numbers. Well, okay, maybe addition. And then the group homomorphisms are functions that go between groups. So they're functions of the underlying sets that go between groups. And they preserve, so you might remember that groups are sets with the multiplication and an inverse operation and an identity operation. And group homomorphisms are just functions of the underlying sets that preserve the multiplication and the inverse and the identity element. So definitely going between different groups. Yeah. Was there another question? Yes.
So for like the category of like propositions, so like A implies B is an implication, but it's also like a proposition, A implies B. So is there like an object corresponding to A implies B and also a separate morphism, or is it like?
Yes, definitely. Yes, we'll get to that later. Yeah. Yeah, so that's why I said that derivation is kind of like the proper notion. Because that's something that says, okay, you start with P, you can get to Q. Implication, when I say P implies Q, that's the proposition itself that you just said. So then that's an object in the category actually. So
Okay.
yeah. But they're usually equivalent in the logic. Okay. So I want to mention top. So this is topological spaces. So like a sphere, a torus, things you might have encountered in your everyday life. Topological spaces with their appropriate notions of maps that you've seen if you've taken a course on algebraic topology. This is a continuous function. And I just want to point out, just for historic interest, that group category theory was maybe invented to say that there's a very special functor a very special relation between the category of top and the category of group that is the fundamental group. And that's how a whole discipline called algebraic topology or homotopy theory started. And that's also how category theory started. They invented category theory to kind of capture the relation between this category and this category. Okay, so just like in computer science, maybe our favorite, like our foundational category theoretic fact is the Curry-Howard correspondence. Like the categories are the same. The correspondence between these two guys, they're not the same, but there's a very nice relationship between them that starts algebraic topology. Okay, and then you have a category of like anything else you want, like rings, vector spaces over a given field, anything mathematical usually forms a category. Also anything in theoretical computer science. So let's get back to those kinds of examples. So maybe I'll write down something that doesn't use the same words as this example, but think about this example under the, I guess I'll say proofs as program paradigm. Maybe people call that also the Curry-Howard correspondence, but in these lectures I need something very precise by the Curry-Howard correspondence. So proofs as types as programs, that paradigm says we can interpret types as program specifications. So we can think of this example, we can just write it slightly differently and think about a category of program specifications, where the objects are program specifications. So I leave it to you to define precisely what exactly that means, as with the rest of the examples. And the morphisms are programs that turn any program, kind of long now to write out, any program needing one specification,
You can erase those in the third session.
oh, okay, thanks. Okay, so the morphisms are programs that turn any program needing one specification into a program needing another specification. Here's another example. Type CH, which is supposed to stand for type theory, where the objects are type theory. So remember I said, okay, pick your favorite type theory. Now we can form a whole category of all the type theories and morphisms that translate between them. Yes?
Can you give an example of such a program that transforms the program?
Yeah, so maybe the specification is to produce a natural number. That's one specification. Another specification could be to produce an even number. And then the program that transforms programs meeting the first specification to the second specification just multiply the number by 2. Or you can think about, I don't know if you've heard about like complexity, like P versus NP, and how they categorize all those complexity levels. Like they're always talking about how to use solutions for one really hard problem to find solutions for another really hard problem. Yes?
So can morphisms be objects themselves?
Definitely. Yeah. We may or may not get to that in the lecture series. But basically like anything, like here, for instance, I'm about to start talking about a category where the objects are categories like this. So like really almost anything can assemble into a category where those things are the objects. Yes?
When you say specification, is that related to the specification like text system analogous, or could it also be like equal specifications?
Okay, I would say that definitely specifications in terms of type theory, well, category, I'm not sure. But probably I would bet that like any notion of specification can be turned categorical. Might require some certain but okay.
If you're working with a category that you found somewhere with data, what would be a warning sign that you've chosen a bad notion of what the error would be? So like, for example, with topological spaces, you might be able to get like relations between topological spaces that are continuous instead of functions. Or maybe like we have, use bijections to require them to be continuous in one direction and not the other. Like there's a bunch of choices that you could make. How do you know that like you probably chose the wrong one when you go back and make work?
Yeah, that's an interesting question. I guess I like the idea of category theory as just being a language, like a formal language, for how we do math naturally. So before category theory came along, people were definitely thinking very hard about topological spaces and continuous functions between them all the time. They didn't have a word for category then, but then they invented the concept of categories, and then they saw that those topological spaces and the continuous functions between them assembled into a category. So they're already working with these things, topological spaces and continuous functions, a lot already. So I think in general, we want to choose a category that includes all the stuff that we like. Yeah.
Do you think it would be pedagogically helpful? What's an example of like a failed category? Something where you've got sort of objects, you've got things that look like, what's an example of something that's not a category?
That's a good question. Okay, so I'm a category theorist, so I live my life by the maxim that everything is a category, everything is a category. But I think the one thing that makes me very, very nervous is that probability doesn't form a category very well. Because the Bayes rule kind of looks like implication, but when you divide by 0, bad things happen. So, well, I haven't talked about transitivity yet, but we want some kind of transitivity in our category, and that doesn't satisfy it. So, yeah, I feel very nervous when I comment on that with probability for that reason. But almost everything else forms a category.
Are there any sorts of, categories where you have, like, really similar to the same ideas of objects between them, but then, like, two separate missions that are more useful?
Yes. And when you have two kinds of, two notions of morphism, those are, well, they have to have some compatibility, but then that's called a double category. Yeah. So I said that sets. So I talked about relationship because that's the first word that I started using. So the category of sets has sets and functions. There's another useful category called rel that has sets and relations. So it's the same objects but different morphisms. And it's very useful to consider the double category of sets with two kinds of morphisms, functions, and relations. That category is closely related to topos theory in the sense that it's not used very much, but a lot of the things that are proven in topos theory, if you've heard of that, which is a big and long-lived field, can be proven using the double category of functions and relations. Yes?
There could be a category of all categories, right?
Yes, there can be. So just like I talked about how in set, we have a collection of all sets. And by collection, I might mean something like that, but we have a set of all sets, so it's not very good. But then we can just choose like a size constraint to solve that problem. We can do the same thing with categories.
Okay.
We definitely have a category of all categories.
Thank you.
Yeah. Good question, all very good questions. Yes.
The morphism of the category calculated space is just
Continuous functions. Yes. Any other questions? Yes.
This is more of just an observation of, maybe it's a weird question that doesn't really work, but like with set, so the objects are sets. So I can think of like, I have the set of integers and functions from integers to a set of, what's the thing that I say? Set of apples. I don't know.
Okay.
So can I also think of these two different sets as also being like their own categories? So I have a category of integers?
Yeah.
Okay.
Yeah.
So in that case, like if I have a category of integers, the functions that I'm describing, are they like closed in integers, or it's like it can only be functions from integer to integer?
So in the category of sets, we are definitely considering functions between two different sets all the time. Also, I mean, functions from one set to itself, but in general, functions from one set to a different set. For a particular set, we can form a category where the objects are the set that you're considering. So like the set of integers, so the objects would be integers. And then the morphisms would be nothing, or almost nothing. I'll get to the almost in a bit. So almost nothing, because like the integer, the set of integers is just the integers. There's nothing else there. So we wouldn't want to add any morphisms, because there's no like extra data that we could encode in the morphisms, except for some stuff that I'll talk about in a second. So we call that a discrete category. So it's discrete in the sense that it's just a bunch of objects without any relations between them. Yeah. Yes.
So there was a question posed right now. What is not a category? So I was wondering, how do you figure out if, like, how do you prove that something that is not a category? Like, you can prove that something is a category by finding a morphism. How do you prove that on this?
When I answer this, what is a category, I will give a rough answer. I'm just going to give a more precise answer in a second. So even in the more precise answer, we start with this data, and then we have some extra stuff that the data should satisfy, which gives us the extra morphism that I was whispering about. So if you want to say that something is not a category, maybe you want to pin down what the object and the morphism should be, and then you can prove, like give some counterexample that the axioms I'm about to list don't hold.
But maybe like you haven't just found out the right morphism, right? Like you have a collection of objects and you're trying to prove it can satisfy that category. So you just maybe not have the correct morphism first. And you prove that it doesn't use that, like it won't form a category.
Yeah, so if you have a collection of objects and you're trying to find the right morphisms, you could, for instance, form the discrete category. Like you just consider kind of a set of those objects, and then you can form a discrete category. That would be a category. So given any collection of objects, there's always like a trivial categorical structure. There's also like another kind of trivial categorical structure that's like instead of like the least amount of arrows, like none, you could give like all the possible arrows. That's also kind of trivial in a sense. So there is always a categorical structure for any given collection of objects. Question is, can you come up with an interesting one that you can prove interesting here, but something like that. Yes.
There's a description that says, is there a notion of a subcategory as in the previous description of the discrete category of the set of integers? What about the power set of the integers with mass within those sets?
I'm not sure what the question means. So, yeah, maybe you can answer that. Yeah, so I mean, maybe the person is asking, I said like in the category, in the set of integers, there's no obvious notion of morphism, like there's no structure there that you can capture with the notion of morphisms, so then we just say there are no morphisms. Maybe this person is saying like in the power set, maybe there's some natural notion of morphisms, and yeah, then you can form a category with that notion of morphism. Which maybe it's like inclusion of subsets. Definitely. Okay, yes?
I was just going to ask if there's any kind of deep fundamental connection between the discrete topology and the discrete category.
Oh yeah, definitely. Maybe you can ask me that question like on Thursday.
Yeah.
And please ask me the question whenever I get to injunctions, which I'm not sure actually right now how long that would take me. Yes. Any other questions? Okay, very good questions. So here's some more examples. So like I was saying, we could take for a fixed type theory, like maybe the one that Anya presented last week, we can form a category where the objects are types and morphisms are functions. But like I said, you need to fix a notion of type theory, so why not take them all? Then you can have a category where the objects are type theories. Maybe I still leave it up to you to define exactly what a type theory is, actually.